I wanted to do a quick lab introduction. So in addition to going over the lab board that we have and getting into the labs, I wanted to talk about some background of some non-ideal effects that are things that we should mention before we embark upon our lab assignment. Some of these are really important when using actual equipment. It's important to sort of draw a distinction between the ideal things that we've talked about in class and the textbook and non-ideal things that show up in labs. The first thing I want to talk about is isolated versus non-isolated supplies. So in the textbook, a supply is just this ideal thing. It's this, a voltage supply is this floating object that always produces a voltage between its terminals. You can connect it to anything, you can connect it any way you want. And as long as you don't put two voltage supplies in parallel with a different value or a different orientation, then you're fine. You can do anything you want with them. So, and with current supplies, same thing. It just maintains a current, it could be whatever it takes to maintain that current, any voltage, and as long as you don't put it in series with another current supply that's either a different magnitude or in a different direction, then you're fine. But in reality, that's not how supplies that we buy tend to work. So if you look in the labs, you'll see a lot of benchtop supplies, and those benchtop supplies will have potentially 3 outputs. And those 3 outputs will, usually you'll be able to adjust the voltage values, and you might assume, okay, there's just like we have drawn here, right? There's a set of terminals here, a set of terminals here, a set of terminals here. You might assume, it's just a voltage supply. You can connect them any way you want in the circuit. But in fact, a lot of supplies are non-isolated, which means that each of the voltage supplies that it has, or current supplies that are in the piece of equipment, they're not actually separated from one another. There's some limitation to how you can configure them, in the sense that there's some limitations either on the range of voltages between the supplies that can exist. One supply might not be able to be 1,000,000 volts higher potential than another supply. Or there might be something like the ground terminals, the negative terminals of the supplies. Internally, those negative terminals may be connected together. So this is quite common, where internally the negative terminals of the supplies are connected. And so you can't just do whatever you want with the supplies. Let's see if this is the case. Let's see what happens if you try to build a circuit. So I just pulled this circuit from last chapter's, from chapter 4, I should say, from chapter 4's material. Let's say you tried to build this circuit using a non-isolated supply. So you had connected a 100-volt supply here between these terminals and a 50-volt supply here. And again, these are 2 supplies on the same unit. And you'd constructed this circuit on a breadboard and connected them together. Oh, and you also had a current supply, which you'd connected here. And it set it to whatever current you needed. You might say, okay, good, this circuit is built. I've built my circuit. And then you might start testing it, and you might start measuring things, and it's a little bit off. It's a little bit off from what you anticipated. And you might not really realize what's going on, right? You sort of say, well, why, maybe you measured the voltage across here, and you got that there was no volts across that resistor. And you say, what? How could that possibly be? There's no way that's the case. Well, what happened is, if you were building this circuit using a non-isolated supply, that actually it's possible that internal to that supply, these negative terminals were tied together internally, which meant you essentially put a short circuit across these 2 resistors. So when you built this circuit, you didn't realize it, but because internally those supplies were connected, in effect, you shorted those resistors in your circuit, and you ended up getting a different answer than what you anticipated. This is the reason why isolated supplies are quite useful, and especially for building the kind of abstract circuits that we talk about in this class. It's really nice to have supplies that are isolated from one another, so that we can put the supply however we want, in whatever configuration we want, wherever we want to toss a supply in a circuit, we can do it. There's another thing I want to talk about with supplies, and that is power supply quadrants. So an ideal voltage supply, or ideal current supply, we describe these as being able to apply whatever current through its terminals are necessary to maintain a voltage, or whatever voltage across its terminals are necessary to maintain a current. In reality, not all supplies can do that. The other thing is, when we analyze supplies in this class, quite often we'll say, find the power for the supply. Is it generating power, or is it dissipating power? Is it I forget all the terms, right? There's a ton of them, right? Is it delivering power to the circuit? Is it dissipating power? Is it drawing power from the circuit? I don't know. There's a million ways to describe positive and negative power. But basically, sometimes we say, here's a circuit. We got a bunch of supplies in there. you analyze the circuit and tell me, does this supply have a positive or negative power? Well, not all supplies are actually capable of having a positive or negative power. So many supplies are only capable of providing current flow out of the positive terminal. They can't have current flowing into their positive terminal, which means many supplies are not capable of dissipating power. That's the case with the supplies that we have in most of the labs in our labs. And usually that's because the people who make the supplies say, well, this is a power supply. You're connecting this to a circuit. You're powering a circuit with this thing. It shouldn't be dissipating power. And normally that's a good assumption. But again, for the abstract circuits that we like to deal with in this class, that doesn't always work. And quite often it doesn't work. And so when we talk about supplies, we have there's a common terminology used called quadrant references. Quadrant references are ways of sort of quickly describing in what operating ranges the supply can work. So on this, we have the positive voltage side of this quadrant. We have the negative voltage side. This would be sort of the x-axis here. And then we have positive current and negative current making up the y-axis here. So quadrant 1 is probably the most common quadrant you see. This is where a supply is producing a positive voltage, and it also has current flowing out of the positive terminal of the supply. So it is delivering power to your circuit. It's delivering power with a positive voltage relative to its terminals. So this is the standard. This is like what a typical your 5-volt supply connected to a resistor. That's what this would be. Another case, though, is what if instead of producing just positive voltages, what if a supply is also capable of producing negative voltages? This would be in the case of like if you have an adjustable supply where you're able to vary the voltage produced by the supply and go positive to negative. So that is keeping the same terminals of the supply in place in the circuit, you're able to transition the polarity of those terminals to negative without physically switching the terminals of the supply. That would be quadrant 2 if you still have positive current flow in this while transitioning negative. I'm next going to talk about quadrant 4. Quadrant 4 is when you're providing a positive voltage, but you have current flowing into the positive terminal of the supply. So this is where your supply is maintaining a positive voltage relative to its terminals, but there's actually current flowing into the positive. So the supply is actually dissipating power. Now this is, again, not most supplies cannot do this. So even if it's a positive supply, which is the most common, not all of them can dissipate power. This in the laboratory, in our main freshman year laboratory that you might have had a class in if you were taking it back in the time when we had class in the labs. The supplies there are not capable of operating in this quadrant 4. They can't do that. And actually, the programmable supplies, most of them we have aren't capable. You're not capable of programming a negative voltage, so they also can't operate in here. So most of our supplies work in here. Quadrant 3, this is where you provide a negative voltage relative to your terminals, and you're capable of having a negative current flow out through those terminals. So that's the most rare by far of all the quadrants that we have. I'm going to clean this up, and I want to talk about the supplies that we have for the lab boards for this class. The lab boards for this class are designed to operate like this. So they are fixed voltage supplies. They are fixed. We have 2 fixed 7-volt supplies and 1 fixed 3-volt supply. Because they're fixed voltages, you can't go negative. You can't have a negative voltage. However, you can just flip the terminals of the supply. So you can in effect hit these quadrants here by just flipping the supply upside down. But it should be noted, if you have to manually flip the terminals, that is not considered operating in quadrant 2 and 3. That's just considered flipping the terminals of your supply. However, you can only just flip the terminals of the supply usually if you're capable of operating with both positive and negative power. So our supplies operate in this range, and we can simulate quadrants 2 and 3 by flipping the supply's terminal orientation, but that's not technically the same thing. That's cheating. So we can't just punch a button and change the value to negative. And this is though very useful, right? The fact that we can operate, the fact that our supplies can operate in quadrant 4 allows us to make pretty much every single circuit that we work, every single type of circuit that we work with in this class. The supplies on our lab board are also isolated supplies, and that means that you can put them in whatever orientation, wherever you want in your circuit, and they are all isolated from each other. They're all isolated from the voltage and current measurement circuits on the board as well. So they're each supply is just a floating, it's a floating supply, totally isolated from all the rest. And we produce that at great expense. It's not cheap to make supplies isolated. Most of the circuitry you see on the board is the result of needing to have isolation for these supplies. If all we had was, if we had just 3 or 4 non-isolated supplies, it would be a very cheap, very simple, very easy board. I wouldn't have spent the last 2 weeks assembling these things if it were that simple. But in order to be able to build the types of abstract circuits that we like to do to demonstrate these concepts we talk about in this class, we really want to have that isolation, and we also really want to have that 2-quadrant operation. So this is typically what are referred to as 2-quadrant supplies are either a supply that is this or a supply that is this. These would both be called 2-quadrant supplies. What is really nice is a 4-quadrant supply, which is capable of operating in all 4 of these quadrants. We actually do have 4-quadrant supplies in the Power Lab. The Power Lab has supplies in there that are explicitly called 4-quadrant supplies. And what that 4-quadrant supply means is, it means it is a programmable positive and negative voltage, and it is capable of both absorbing and delivering and dissipating power. So just a little brief background. I want to talk about these non-ideal effects, and we will talk, I'll talk also in this video about the actual lab board itself, how to set it up, how to use it. So today we're going to be going over the lab board that we're going to be using for the entire quarter. First of all, I want to show you what you're going to get when your lab board arrives, if it hasn't arrived already. You're going to have the main board itself. You're going to have a USB micro cable, which is used to power the board. You're going to have a package of wires that can be used for breadboarding. You're going to have a package of various components, mostly resistors. You got a couple of op amps in there and some terminals. And you're going to have the breadboard that we use. So first of all, let's just go through assembly of the board itself, because there's a little bit of assembly that you need to do. The breadboard is designed to completely cover the kind of tacky Viking with a face mask logo that I made. So it kind of gives a nice indicator of where to put that breadboard if you're using it. You don't have to stick the breadboard on. The breadboard has a sticky adhesive back. If you do plan to stick the breadboard on, and I will, I would highly recommend you not remove all of the adhesive. So you don't need the full adhesive to attach this thing to the back. You can just use a little pieces of it. And so I can show you how to do that. You know, if you just peel back the corners of this thing, and if you just snip the tape off the corners, I'm going to do this off video for a sec.
But the idea here is if our breadboard ends up going bad and we need to replace it, it's better not to pry the entire thing off, because these are very adhesive. So these are very good at sticking to the board. And really, it's not like this shouldn't be really encountering any kinds of strains that prevent it from, that sort of pull it off anyway.
So what I did is I just kind of cut the corners off of that, and then I can flip it around, and there's not really an up or down here. And then I can line it up with that square on the board there, and maybe I'm being a little too perfectionist with it, but there we go. Push it in place, and then that's very rigidly connected now, just with those corners exposed. And the nice thing is now, if we need to undo this, we can pull it off fairly easily. The next thing is the connectors for the current meter, the COM and the 50 and the 50 volt and the 50 milliamp. Some of you may have received some banana terminals in your bag. Others of you didn't. So we have the posts that connect for the multimeter portion of this. They are capable of taking 4mm banana plugs. but banana plugs aren't necessarily the most useful thing to connect just for a small breadboard. It's not, you know, usually a bare wire is fine, so not everybody needs it, but not everybody necessarily got those banana terminals. So I'm going to show you what I do. So I am going to open up my pack of wire, and I'm going to choose a fairly lengthy wire. I'm going to choose a yellow wire for my common, and I'm going to choose 2 orange wires, 2 long orange wires for my current and voltage measurement. Oops, not 2 long, or sorry, 2 reds, 2 red wires here. Okay. So to secure these wires into the terminals here, there's several ways to do it. I kind of like just to push the wire through the little through hole. So the wire fits through this through hole on the, you see how it kind of went in there like that? And then we can just kind of fold it over a little bit. And then we can take inside the bag, you'll see there's these little red and black terminals here. So these red and black terminals here, these are going to actually screw into the board here. So, oops. So we can take this terminal now and just with that wire through there, we can actually just poke this thing through. And then on the back side, we can put the washer. Oops. On the back side, we can put the washer and the nut here. I apologize. I've done videos like this in the past, and students always complain my hands are kind of gnarly. My hands have been injured in the past, so I got a bunch of scars on there. So sorry for my gnarly hands, but not much I can do about that. Okay, so I'm just securing that, and that's good enough. So now what we have is we have a wire in the common terminal, and we can also connect 40 millimeter plugs here, but this wire is, we can use as a common reference for doing voltage and current measurements now. And I can repeat this process for the other 2. So I'll probably skip the video or magic a television this thing for the rest of these. Okay, so we have our 50 milliamp current wire here, we have our common wire, and we have our 50 volt wire right here. So pretty much everything we need. So let's move this off to the side a little bit. Now, just like any other multimeter, you do not want to measure current and voltage at the same time. So you want to only measure one at a time. This is set up to automatically, if it detects a current flow on the current meter, it will switch to a current measurement. If it detects no current, it will by default just measure voltage. So before we power this thing up, let's talk about what we've got on this board. So we have a microcontroller up here. That microcontroller, you might recognize it as an Arduino Nano. All it does is it just drives the LED display. It reads basically a value off of an analog digital converter that's external here, reads that value, does a little math on it, and displays it here. It does some of the switching and detecting button presses and things. It's just the brains. It's not actually, though, it doesn't actually interact with it doesn't control our circuit at all. So basically, this bottom half of the board is completely separate from the top half. This bottom half is the power supplies that are all isolated. The top half is the actual measurement, basically a multimeter. But the two are separate from each other. They can be powered by the same thing, though. There's a switch here. This switch, when it's in the up position, means that the power from this board is connected to the power for this board. So we can power this whole thing from one switch, from one input here if we have this switch up. You should basically only ever have to have this up, and you really should never connect a USB up to this one. You can, if you do connect a USB to this one and to this one at the same time, this switch has to be in the down position. If it's not, you will break the thing. Or you can do some serious damage to your computer you're connected it to the board itself as well. So for the most part, leave this switch where it's at, leave it in the up position, only power it by this switch here and you'll be fine. If you do want to like program the Arduino and hopefully not break it, it is still a fully functional Arduino Nano if you need to use it. So on the board we have, and I don't want to power anything up yet, we have a main power switch. This power switch, if it is in the left position, it cuts power to all of these supplies. If it's in the right position, it powers all of these supplies. You can also individually power the supplies. So each supply has its own power switch as well. The supplies have a light indicator to show whether or not they are operating properly. You should notice that the current supply, its light will only turn on if it's able to have a current flow. So basically, if the current supply, which is this bottom one, is not configured in such a way that current is allowed to flow, the light will be turned off. Up here, we have a 3-volt supply, a 7-volt supply, another 7-volt supply, and and these are all voltage supplies. This bottom one is a 1 milliamp current supply. You can see on the label here too, you can see there's a little picture and it shows the value here. So basically, you can treat these just as any isolated supply. That is to say, the voltage difference between this terminal and this terminal will be 3 volts. The voltage difference between this terminal and this terminal will be 7 volts, etc. You can connect it any way in your circuit you want, and that'll work just fine within reason. There's some limitations, which we'll talk about in later labs. All right, let's power this thing up. Let's actually get this thing going. So I am using a battery pack for this, but all it takes really is a 1 amp 1 amp USB power source. We're going to plug our USB cable in here. All right, and you see it first of all turns on. So right now, this value that it shows, it's showing like negative 1.4 millivolts here. And I know you can't really see the millivolts because of the light. That's just random noise. That's just noise that it's picking up from the room that I'm in. If I touch these terminals, it's going to change, right? It's not actually connected to anything yet. It's just floating there. So it's just whatever floating voltage it's getting is what it's showing. You'll notice there's 3 lights that are turned on right now. The 3 volt, the 7 volt, the 7 volt have their light turned on. That's because these are all turning on. These are all producing the proper voltage. The current supply is showing nothing. That's because it's not wired in such a way that current can flow. If I want to short the terminals of this current supply, then it will allow current to flow and then that light will turn on. But for right now, because of the way it's configured, it's not doing anything. And doesn't actually have 1 milliamp flowing through it, so the light is off. We can turn each one of these, we can turn all the supplies off by flipping the top switch. That turns them all off. We can turn them individually on and off by switching their own switch, so you can see those lights come on. It should be noted, a supply that is turned off is not the same as a 0-volt supply. So turning the supply off is not the same as setting it to 0. It's just basically, it's not powered, it's not energized. You don't really know what it's doing. So you still need to disconnect it from your circuit if you're trying to disconnect it. All right, let's jump right into it. Connecting to these let's measure a voltage first of all. So connecting to these voltage supplies is a simple matter of, you have spring terminals here. So you can depress the spring terminal and insert a wire, and I should be able to do it with my finger. These are kind of tough to push though. See how strong my nail is. Yeah, so you can depress that, and then once you've depressed that terminal, you can attach a wire, and it's spring loaded, so it'll hold that wire in place. Let's put another wire in here. Now I'm not being deliberate about my color coding here. Okay, but I've got 2 wires now. So I've got 1 wire connected to the top side of my 3-volt supply, 1 wire connected to the bottom side of my 3-volt supply. I'm just gonna, just for safety's sake, I'm gonna connect these wires to 2 rows of my breadboard here. So I'm gonna connect this wire here to this row, and this wire here to this row. So now, this row of the breadboard is my positive 3 volts. This row is my negative terminal reference of my 3-volt supply. It's not ground though. There really is no ground in these boards. They're just floating supplies. So let's say we want to measure these supplies. Let's say we want to measure this 3-volt supply. If I connect the red voltage side of my voltage meter to this terminal, to this row, and I connect the common to this row, I should be able to measure the voltage across this. So let's do that. Let's do the wire. Oh, sorry, this is my current supply. This is my voltage supply here. So we have to connect the wire from the supply that says 50 volts. We will connect that to this top row, and the common wire we will connect to the bottom one. And then immediately you see this measured voltage goes to 2.995. Well, that's close enough. That's pretty close to 3 volts. Keep in mind, I'm the one who calibrated all these boards, so if your board is way off, that's my bad. But 2.995 volts is really close to 3 volts. We'll call that pretty good. So we're measuring the supply. It looks pretty good. It looks like a nice stable 3 volts here. If we want to, we can take a resistor and put it across the supply. So if I take a resistor and have this resistor connected here, looks like we are still getting 2.995 volts. Again, these are regulated supplies, so they should maintain about 3 volts. This one's 3, the other one's 7. And so this is the basics of measuring. Let's say we want to measure a current. So right now we have 3 volts flowing through our resistor. Our resistor is still connected. Whenever you want to measure current, you have to break the circuit. So it's a little hard to see right now, but what I will do is I will one side of this resistor, I will move one side of this resistor to a different row. Maybe if I bend the resistor over, you can see. I moved one side of the resistor to a different row. So essentially, now I've broken the connection between the top side of the supply and the top of the resistor. And if I want to measure the current, I can connect the red terminal 50 milliamp to the positive side, and then my common terminal can be connected to the top of that resistor. So I broke the circuit, and now I'm forcing the circuit to flow through the current supply. And it looks like now I'm measuring, now you'll see the light change. Now the light that is illuminated is the milliamp light. It's showing 2.994 milliamps of current. So my guess is that was a 1K resistor. I didn't check, I just pulled it. But if we applied 2.995 volts and we are now reading 2.994 milliamps of current, well, I probably just connected a 1K resistor in series or to this 3 volt supply. Now one thing to note, these supplies are isolated, so we can play whatever games with them we want. Let's go back to measuring voltage. So I'm going to disconnect my current supply, and I'm going to go back to measuring. So I'm going to put this resistor back in the circuit, and I'm going to go back to measuring the voltage across that resistor, which is the voltage of the supply. Okay, 2.99, we're back up to 2.995 volts. So we have volts, millivolts, milliamps, microamps of current. Let's say we want to get a 10 volt supply. Well, we don't have a 10 volt supply. We have a 7 and a 3 though, and these are isolated supplies, so we can connect them together. So if I want to create effectively a 10 volt supply, I can, oopsies here. Let me just disconnect this. You get to see me fumbling with a breadboard here. So I'm going to disconnect that negative terminal, and I'm going to connect the negative terminal of the 7 volt supply to the bottom of the resistor. And then I will connect the positive terminal of the 7 volt supply. I'm going to connect the positive terminal of the 7 volt supply to the negative terminal of the 3 volt supply. And I really should de-energize this while I'm working. This is bad practice. Always de-energize the circuit while you're working with it. So always remember to do that for safety, for both safety for you and safety for the board. Now I'm going to put a jumper wire here. And again, I'm being a little awkward because I'm trying to keep this on video as I do it, but I'm going to connect a jumper wire from the negative terminal of from the positive terminal of the 7 to the positive terminal of the 7 to the negative terminal of the 3. I'm not sure you can see that. And sorry, I'm powering it by a battery, and the battery just randomly turns off every once in a while. Okay, so now I have the negative terminal of the 7, positive terminal of the 7 is connected to the negative terminal of the 3, positive terminal of the 3 is here. So my voltage difference between here and here should be 10 volts. Let's find out if that's true. Let's energize the circuit. And yes, 9.994 volts. That's pretty close to 10. So by connecting these supplies in series, we were able to get 10 volts by combining the 7 and the 3. But the cool thing here is these are isolated supplies, so we can actually we can connect them in any orientation we want. So let's make a 4-volt supply by taking the 7-volt supply and connecting the positive terminal of the 7-volt supply to the positive terminal of the 3-volt supply, and then connecting the negative terminal of the 3-volt supply to the top of our resistor. So essentially we have a 7-volt supply oriented right side up and a 3-volt supply oriented upside down. So I'm going to de-energize the board, and I'm going to flip around this connection to the 3-volt supply. So the positive terminal of the positive terminal of the 7-volt supply is now connected to the positive terminal of the 3-volt supply, and the negative terminal of the 3-volt supply now we're going to connect to our circuit. So I don't know if that shows up on video, but we have this brown wire. Maybe brown's not the best color. Positive terminal of the 7 connected to the positive terminal of the 3, negative terminal of the 3 connected to our circuit. Let's energize this and see what voltage we measure. 3.997, that's pretty close to 4. So we have essentially generated a 4-volt supply. We've essentially generated a 4-volt supply here by taking a 3-volt supply, connecting it upside down. And again, that's not normally something you can do. That's only because we have 2 quadrant supplies here that are capable of dissipating power. So right now, that 3-volt supply is dissipating power. It is burning off power. So that's the reason for all these electronics in here, is so that this is actually capable of dissipating power. But the cool thing is we now get 4 volts. Let's go crazy. Let's make the biggest voltage we can. Let's turn this off and let's connect the 7 volt, the bottom of one 7 volt to the top of the other. So we'll connect the bottom of one 7 volt. I'll use a yellow wire now, so it's a little more clear. So okay, so now we probably should be making this connection on the breadboard itself. I'm playing a little fast and loose here with the jumper wire, so don't be like me. It's a good recipe for breaking something, but I just want to really quickly just give an introduction to this board. So, okay, so now we have the positive of this bottom 7 connected to the negative of this 7, the positive of this 7 connected to the negative of the 3. So this should be 7 plus 7 plus 3. This should be 17 volts. Let's see if we're able to generate a 17-volt supply here. Let's see if we're able to generate a 17-volt supply here. So. 16.99, that's pretty close to 17. So I'm going to show you another feature. Let's say this thing is wiggling around a lot. Let's say your voltage measurement's wiggling around a lot. You can, if that's happening, hit this button and switch to high resolution mode. So hitting this button, that's low resolution, that's high resolution. High resolution mode basically just averages more data samples. So if you have a noisy measurement, especially if it's a small voltage or a small current, it's going to help you kind of clean that up a little bit. So it's going to help you. It's going to smooth it out. So if you notice your voltage or current measurements jumping around a lot, you can hit this button until you see the high, and that means you're taking a high resolution samples. It's just averaging more samples together. Some other things. So let's de-energize this. So that's the high resolution, low resolution. De-energizing the board here. Now notice how slow that drops. So when we're in high resolution, I'm gonna turn it back on. When we're in high resolution, look at how long it takes for that voltage to creep up to its proper value. That's the downside of averaging over a lot of samples to get a nice smooth value, is it moves slow. So when we turn this board off, look at how slow that number drops. Now let's compare to low resolution. Low resolution, so that's millivolts, we're down to point something millivolts. We turn it on, whoop, it jumps basically right up to 17 in low resolution. And it drops almost immediately down into the millivolt range. So low resolution is a faster response to the measurement. High resolution, though, is high resolution, you're going to get a more accurate value. You're going to get a smoother, a less noisy value, I should say. But it takes longer for high resolution to switch back and forth. So a couple of things. The lights on these supplies are not just for fun. The lights on these supplies are a good indicator for you as to whether or not the supply is working properly. You see a nice illuminated light, it means everything is probably okay with the supply. These supplies do have a little bit of protection, so always check your circuit before you connect it. Always check your circuit, make sure you're not going to accidentally break things, but make sure your circuit's correct before you energize it. But these supplies do have a minimal capability of, if they encounter a short circuit or something that could possibly damage them, they do have a little bit of protection, a little bit. It is still possible to break these. So let's look at a case where we do something stupid that might break your circuit. So, I'm just going to switch to pressing. If you have like a little screwdriver, that's great for depressing these spring posts here. A fingernail, I don't have enough collagen or something. My fingernails aren't really good at it. So I'll just fully disconnect this circuit here. So let's do something dumb. Let's do something dumb, like let's short the terminals of the 7-volt supply. Don't actually do this on yours. But let's say I had shorted the terminal of the 7-volt supply. Okay, shorted the terminal of the 7-volt supply. Big no-no. You can't really see that because I did blue on blue. Let's see what happens when we fire this thing up now. When I turn this, when I energize this, this supply is shorted. These other ones are not. And you'll notice the light for this one does not turn on. The light for this one is off. And that's one of the ways that the lights serve as an indicator of something's gone wrong. So if you look at the lights and they're really bright or they're off, turn off your circuit immediately. Something's wrong with your circuit. You got to go back and check. So again, the protection of these circuits is not perfect. You have a little bit of protection, but you also only have one circuit. So if you mess this thing up, you fail the class. No, I'm just kidding. I don't know what we do if you mess this thing up. So we remove the short circuit, turn it on, and boop, now all the lights come back on again. Everything should still be good to go. Any other features of this board? So this board came calibrated with these 6 potentiometers here. They're adjustable resistors. I would recommend against touching those at all. So it's pre-calibrated. It's pre-calibrated using really high quality instruments. Probably if you notice there's a value that's off on this, it's probably due to the resolution of the board itself, not due to the calibration. So trust that the calibration is correct. Oh, one more thing, the current supply. Let's talk about the current supply. So de-energize the board. Oh yeah, before I got too far, I'm scatterbrained today, sorry. Yeah, so don't adjust the calibration. We did the calibration. The royal we did the calibration for you before sending these boards out. It should be correct. If you think the calibration's way off though, email me and we can talk about it. If yours is just like you're measuring just crazy stuff, let me know. Okay, so let's use a color wire that you're actually able to see. Let's do the current supply. So the current supply, it might not be able to do a 1K resistor. Let's just short the current supply. So it's okay to short a current supply. Current supplies are perfectly happy being shorted because it's actually very easy for a current supply to drive a short circuit. right? I mean, that's, there's nothing to impede the current that it's trying to produce. So I'm just going to connect this current supply to the same row here. I'm going to energize my board. And now you'll notice the light for the current supply turns on now. The current supply light turns on because now current's allowed to flow through there. So if I break the circuit, the light turns off because there's no current flow. If I connect it, now the current supply is happy. If we want to measure the current through this current supply, we can do a quick measurement here. So anytime you want to measure current, you first of all de-energize. You break the circuit. I always break the circuit by connecting it to a different row. Then you have the top, we're going to have this row flow into the current meter. We're going to have the out of the current out of the current meter, the common terminal connect to the bottom side of the current supply. Notice as soon as I energize this, right now we have volts and millivolts. Right now millivolts is illuminated. When I energize this board, the board should detect the fact that there's now a current being measured, and it should switch to milliamps or microamps. So sorry, my power supply, I'm gonna have to find a better power supply. So let's try, let's energize the board, and yep, it switched to microamps, and we're at, now it's switched to milliamps, so 1.006 milliamps. That's pretty, it's a 1 milliamp current supply, so 1.006 milliamps is pretty good. 1.007, that's pretty close to 1 milliamp. We're gonna have to call it good enough. We'll switch to high resolution, see if that helps. Not really, no, it's not really that jittery. 1.006 milliamps of current. So that's our current supply that we're measuring. We're just measuring it using the board. And I think I pretty much went over the basics. We'll talk more about features of this board as we do different labs, but for right now, this is what we got. Now let's just try for fun de-energizing the current supply. And that current drops down to the microamps, 97 microamps, 60 microamps, 39. As soon as that current gets too low, the board's going to detect that that there's no current, and it's going to switch back to measuring voltage. So, but yes, by de-energizing that supply, we ended up seeing the current drop to 0, and it must be on high resolution because it's adjusting slowly here. Let's switch back to low resolution, yeah. So 1.006 milliamps for a 1 milliamp current supply, that's pretty good. Yeah, anyway, 1 milliamp current supply, 2 7-volt voltage supplies, a 3-volt voltage supply. We're gonna have a lot of fun with this board doing different labs. It enables us to do a lot of neat things. The fact that these are 2 quadrant supplies, the fact that these are isolated supplies allows us to make some really nifty circuits that we actually haven't been able to make in the past. So we're gonna be able to make circuits in this class that we were not able to do in previous years. I guess it's kind of a COVID blessing in disguise here. Thanks for watching this introduction. Hopefully you all get your board soon. If you don't get your board, if it comes to Thursday lab time and you haven't gotten your board, send me an email, let me know. We'll try to figure out what's going on because all the boards are shipped. Everybody should see their board fairly soon. Thank you for watching.